Here's our definition of ellipse. What I'd like to do now is come up with a rigorous definition of a hyperbola. It is a collection of points, not the sum, but the difference of whose distance from two fixed points, also called foci, is a constant. Look at this hyperbola. It has two foci, f1 and f2. Here's a point on the curve, or one branch of the curve, where this distance minus this one is some constant. But this distance minus this one is the same constant. Now, I'm not going to derive this out of thin air because it's so darn similar to my derivation for the standard form for an equation of an ellipse, but it is the case that if your center is located at the origin and you branch out left or right, there is the equation in standard form. If your center is at the origin but you branch out up or down, here's a standard form for the equation. Unlike an ellipse, it's not the case A is larger than B. It doesn't have to be. What's important here is that we put the A in a position that it squares below whichever term is positive when it's in one of these two standard forms. If your center is not located at the origin but at H, K, here they are. With one small fix. Now, neglecting translation, although you and I will be spending all our time on translation, neglecting translation, my foci is still located at, in this case, plus or minus c comma 0, or 0 comma plus or minus c. But it's also the case that I have asymptotes located at y equals plus or minus this, or y equals plus or minus this. Now, if you don't want to memorize all this garbage in terms of A's and B's, don't worry, but I'll show you what's going on with an example. It is the case in both these cases, however, this is a relationship among those constants A, B, and C with an ellipse. With hyperbola, very similar, but we're going to get a sign change with the second term on the right-hand side. So let's you and I consider an equation of a hyperbola. Rewrite it in standard form, clearly sketch this graph, and in the graph, label all vertices, all foci, and identify the equations of the asymptotes. Like with my last example, I will co-locate all the terms involved in the variable x. I'll even factor out a 3. Co-locate all the y terms and even factor out a -1. And slough off the constant term. Complete the square on x and compensate. Complete the square on y and compensate. I think it'll easy with this. Now let's graph. Let's see if I wrote it down for you. So here I go. The center is located at H, K, which is 1, 2. Now, if we use that typical high school algebra technique of just building our box, we don't have to. We can get the asymptotes first, but let's go for it. I will move left and right 1 unit because my A squared is 1, so my A is 1. 1 unit to the right and to the left of the center. I will likewise move the square root of 3 units above and below it. That's approximately 1.7. And if I consider such an imaginary box, it is a case that the asymptotes will cross through opposite corners of the box. And the vertices are located on the box's edge. But because of x variables involved with that first term that does not have a negative sign out front, I know I'm going to be in the x direction, or the horizontal direction. And clearly this vertex right here is located at, is that going to be here? Gosh, that's negative, isn't it? Yes, it is. My other vertex located 1 unit to the left of that. There's my other vertex. Now, it certainly is the case, getting rid of these dotted businesses, certainly is the case that I'm going to branch out left to right, hugging the asymptotes at extreme values of x and y. So that's a very, very poor depiction visually of what the second branch looks like. Like I just said, I want to hug the asymptotes at extreme values of x and y. I guess I meant this. Now there's a few things I'm missing. Number one, I'm missing the first focal point, the second focal point, located somewhere over here. Now to find those foci, recall that c squared is equal to a squared plus b squared. Doesn't matter which one's a and b in this case because they're being added. So I'll treat c as 2. But CD equal to 2 means first focal point is located 2 units to the right of that center. The other is 2 units to the left of that center. The only thing I don't have on the board are my asymptotes. So let me come up with the rectangular equations of my asymptotes. Well, I think they're going to look like this. Now, technically speaking, x naught comma y naught are the coordinates of some point known to be on these asymptotes. Notice how the centers on both of them. As far as the slope is concerned, piece of cake. To get from the center to one of the corner points of the box I drew, I'm going to rise root 3 units, run 1 unit. The ratio of rise to run is root 3, but it could be plus or minus. Or shall I say better yet, in point slope form. I should say that. In slope intercept form. Is that like this? Not enough room. In this. So I clearly sketched the graph hyperbola. I identified vertices, foci, and equations of the asymptotes.